Jai Hind everyone. My name is Gunjan Saxena, Assistant Professor Akgec Engineering College in CSC department. Today I am here to continue with the series of DA. So in this particular lecture, I am just telling about the recurrence relations. In this particular relations or solving the recurrence equation, there are so many way to solve these particular recurrence equation like substitution method, iteration method, master method and the tree method. In today's lecture, we are covering about the master method. So let's start. Firstly, we know about what is the recursion. As we all know, or we can say in our first year in C programming, we already learn about this particular topic. So I'm just revising about this. When any function is calling itself again and again in their definition, this phenomena is called as recursion. And this particular function which is calling itself again and again called as a recursive function. So, or we can say every recursive program should have a termination condition which is known as a base condition. Otherwise, the code is gone in infinity loop. In recursion, one function call itself, number of parameter never change. Code will never change, only the parameter values are passes or we can say changes. Recursion is basically solving a bigger problem in terms of a smaller problem. Just like a divide and conquer technique, a huge amount of problem is divided into small chunks and then we solve chunk by chunk and finally we got the result. As the example is lying here, the how we can calculate the factorial of 5, the answer is already known, which is 120. What is the solution actually? First, we have to go the value of 5 multiplying by fact 4. After then, 5 into 4 multiplying by fact 3. What we are seeing over here, fact 3, fact 2, fact 1, there is a decreasing function. Some situations are there, some phenomena are there. By using this phenomena, fact is continuously decreasing. And what is the condition, or we can say when we go to decrease and decrease and decrease until we reach the base condition. So remind us, this base condition is very important. How we can say in a loop scenario, there must be a condition which is going to be break in some point. Just like that, a base condition is the way how we can move from this particular recurrence solution. Okay, I am just taking about the one very important, or we can say very powerful approach. The name is binary search. How this binary search has worked, I am not telling about the complete process of binary search. I am just explaining how we are getting the recurrence relation equation of binary search algorithm. So, I am just brushing up about the binary search function, or we can say process. In this particular process, the huge amount of elements which is already in sorted form, we are just finding the midpoint. How we are finding the lower bound and the upper bound by the 2. Then the mid value is 5 and from this mid, we are just dividing into 2 parts. Okay. So, if we are considering the whole complexity of this particular algorithm is Tn, and this is calculated like Tn by 2 plus 1. How this Tn by 2? Because we are just dividing this particular work in 2 parts. So, if the complete complexity is Tn, then we are just dividing into 2. So, Tn by 2 and dividing as I am just telling all the arithmetic operations like addition, subtraction, multiplication and division always take a constant time in any particular operation. So, for dividing in binary search, here the dividing operation taking constant time of 1. So, the complexity of binary search is Tn equals to Tn by 2 plus 1. Okay. Another example for just calculating how the recursive equation is calculated. Suppose there is any function, or we can say any code from any algorithm. So we are assuming the complete code complexity is supposed Tn, and number of steps involving in this particular algorithm, or we can say steps. So summation of these individual steps is also equal to the complete complexity, which is represented by Tn. So how we are going to calculate, suppose a complete function having the Tn complexity, as we know all the punctuations like curly brackets are there, and the if statement, else statement having a constant time. So this particular if can take a constant time 1. And obviously, if this condition is true, then this particular printf is executing one time, and this is the recursion. Here, function is calling itself again and again. When? कब तक ये फंक्शन हमारा एग्जीक्यूट करता रहेगा? When we reach to the base condition. So we can say if complete process n is here and the complete complexity is Tn, then is particular function n minus 1. So the complete complexity of this particular function is Tn minus 1. Then what we are doing? We are just simply doing the summation of this particular frequency steps, which is Tn minus 1 plus 1 plus 1, which is the constant. So constant we already know it's totally just like a avoided. So the total complexity of this particular equation is Tn equals to Tn minus 1 plus any constant. Okay. Now we are taking the another example. So एक बार इसको भी देख लेते हैं. If suppose we are one function is completing the time complexity of this particular function is Tn, and already I discussed the if is a constant value which is taking a complexity 1, and this for loop, obviously this for loop is going to start from 0 and less than 1. So obviously 1 plus this condition, or we can say loop is moving for n for the true condition and plus 1 is for checking the wrong condition. Okay, so this loop having n plus 1 complexity, and this printf already checking for n element. When the condition is wrong, obviously printf is not working. So n over here, and this particular fn, as I earlier discussed, Tn minus 1. When we are summation these particular thing, the answer is Tn equals to Tn minus 1 plus 2n plus 2. So the constant is discarded. Here two constants are there, this 2 and this 2 will be discarded. So the total complexity is Tn minus 1 plus 1. So this is on our screen. This is the very famous example, which is the Fibonacci series. So how we are going to calculate, or we can say how we are calculating the recursive function for this particular Fibonacci series. Let's check. For this particular if, as I already know, the time complexity is 1, and this particular return here fib n minus 1. As I earlier discussed, for this particular function, the time complexity is Tn minus 1 and this particular Tn minus 2 and this plus 1. So what we are doing adding something. So Tn minus 1 plus Tn minus 2 plus 2, the constant is discarded. So the time complexity for Fibonacci series is Tn equals to Tn minus 1 plus Tn minus 2. Now, as I earlier discussed, in this particular lecture, we are just discussing how these particular recurrence equation will be same. So what is the issue? What is the problem? If we are having a normal, we are just having a code addition of two number, or calculating the reverse of any number. If we are having simply iteration based code, then simply we can calculate the time complexity manually. So in this particular recursive equation, this is very difficult to find frequency count for this particular equations, or we can say recursive equation. So in the recursive equation, we need some already existing approaches. We are just going to go through about this. One of them, the approaches, the master method is there. Maybe in another videos, we are discussing about the substitution method, the tree method and the iteration method. Okay. So in master method, basically this is the way, or we can say this is the method to solve the recurrence equation. In this problem, we are divided the number of problem into sub problem, each sub problem having the size of n by b, and need the function time which is fn to combine and or break the solution. We can apply the master method if the recurrence is only in this particular way. So this is very, very important. If our recurrence equation is in this particular form, what was that? Tn equals to a t n by b plus fn, then and then only we can apply master method in that particular recursive equation, where always the value of a and b is equal to 1 and greater than 1. And what about the function? Function is never be negative. It may be a 0 or greater than 0. So, in this particular master method, there are 3 theorems, or we can say there are 3 cases in which our situations are lies. We have to check what are the cases is going to be used, or we can say in which particular case our condition or our situation is arises. Then what are these 3 cases? Firstly, if we are checking for the upper bound, then what we are thinking, we have a 2 function. When we are discussing about the fn, this is the growth of our function which is already given. Then we have to find the growth functions for this particular given function. So the growth of function which is gn, my bad, this is gn. Then how we are going to calculate, or how we are assuming what is the relation between in this particular function. So supposing if we are having fn and we are calculating the bound function of this particular given function, there are 3 ways, or there are 3 situations. What was that? This particular gn may be equal to this function, may be greater than to this function, and may be smaller to this function. So these 3 conditions are reflecting over here. If the fn is greater than our given function, then first theorem is applies. If they are equal, then second theorem is applies. If gn is smaller, then third condition is arises. Suppose gn is greater than, obviously we have to subtract something. Then what was something? This is the epsilon, and this value of epsilon is always be greater than 0. And if our gn is smaller, then obviously we know we have to add something. And what is something? Something again the value of epsilon. So if any of 3 cases arises, then simply these are the solution for that particular situation. Okay. In third case, we have to know if we are adding something in particular gn, then we have to check some regularity condition if and only if this condition is worked, or we can say proved, then and only we can say the time complexity of these particular recursive equation is equal to theta fn. Okay. Now we are just solving some example. By using these example, we got the more clarity. Okay. So in your examination, question arises like this: solve this particular recurrence equation by using master method. What is the step number 1? Firstly, we have to compare this particular equation with our standard equation. What was that? Tn equals to a t n by b plus fn. Just comparing this particular recursive equation with the standard equation, we are just getting the value of a, b and fn. So here a equals to 4 from this particular equation, b equals to 2 and the value of fn is n. Just calculating the gn. How we are calculating the gn? The formula of gn is actually n to the power log base ba. So what was that? N to the power log base 2, 4. We are just rewriting 4 as 2 to the power 2, and in the logarithm the value comes to fronter and the same base, the value is equivalent to 1 as we know, then the Gn is n square and the Fn is n. So obviously Gn is leading to Fn. So we have to minus something from Gn. When we are going to minus something from the Gn, then the case 1 is arises. Okay. Then the formula is Fn equals to big O log n to the power log base Ba minus something. Then simply say here n square and here is n. What we are going to minus, just equating these things. Obviously 1 from n square, just getting the n. So 2 minus 1 equal to 1. So we can say the case 2 is applied and the solution of case 1 is simply Tn equals to theta n log base Ba, and the value of this particular is already calculated, which is n square. So the answer of this particular recurrence is theta n square. Let's take another example. So in this particular example, obviously I am writing here, this is the binary search equation which is already discussed in very first slide. So just checking out. So here the value of A, which is 1, and the value of V, which is 2, and the Fn is 1. Now what we are doing, we are just calculating the value of Gn. Then Gn is n to the power log base Ba and the value of Gn, which is equal to 1. And now just comparing Gn and Fn, which are both are equal. So simply we are saying the case number 2 is arises when Fn is equal to the Gn value. Then what was the solution? The simple solution is, if case 2 is arises, Tn equals to theta n log base Ba in power log n. So the value of this particular already calculated, which is 1, then our solution is Tn equals to log n. Okay. We are just calculating or checking the third example, you know. So what was that? Tn equals to 2Tn by 2 plus n by 4. So first step, as we all know, we are just equating the standard equation and getting the value of A, B and Fn, which are 2, 2 and n to the power 4 respectively. So obviously step number 2, just calculating the value of Gn, which is n to the power log base 2, which is equal to n. So I am just comparing the value of Gn and Fn. As we know, the value of Gn is less than 2Fn. Already we discussed when the Gn is lower than Fn, then case 3 is arises. But we are not directly said if Gn is lesser than Fn, we are just going simply putting the solution of case 3 now. We are have to apply, or we can say if and only if the regularity condition is met, then and only we go to the case number 3. Then this is the regularity condition, which I already discussed in last slide. We are just going to prove this particular equation. So the value of A is 2. Just remember, or just you know, point out this particular value. This is not a Fn. This is actually Fn by B. Then the value of Fn is n to the power 4. Then the value of n to the power 4 by B is obviously if we are putting power 4 at n, we also putting power 4 at B, and the value of B is 4, then this particular Fn by B is equivalent to n to the power 4 by 16. Hope ये चीज समझ आई होगी. Now C and putting the value of Fn. Now by this particular 2, we are just subtracting the values n to the power 4 by 8 is less than and equal to C n is n to the power 4, then n to the power 4 and to the power 4 cancel, and this particular situation is there, and we can say the regularity condition is met. So we can say it has satisfied the regularity condition of the master theorem. Then simply the solution of this particular recursive equation is Tn equals to theta Fn, and Fn, the value of Fn is n to the power 4. Okay, so these three examples are basically a simple and the basic master method example. But one more very important point is there. What was that? Master method for non-polynomial. In this particular point, we are just saying there are so many situations when we are saying our given Gn is like when we are comparing Fn and Gn, then we are saying the Fn is smaller than Gn, but not polynomial is smaller. In another way, we are saying our Fn is greater than Gn, but not polynomial larger. What was that actually? Suppose this is the x-axis. In this particular axis, this is the situation when our Fn and Gn both are equivalent, and this is the case too, if you are watching. In this particular way, we are saying some point is there, Gn is less. Gn is less to Fn, obviously, greater, then we have to subtract something larger. But lekin, in Fn, we are saying Fn is larger, but not a polynomial larger. Okay, in this particular way, Fn is smaller, but not a polynomial smaller. Then what we are doing, there are some gap. What was that? This is the gap. So this gap cannot be directly solved by a basic phenomena of master method. We have to use some extension of this particular master method. What was that? First thing is, obviously our given equation is also in a form of Tn equals to Atn by b plus Fn, obviously, and the value of A and b is always greater than 0. But remember, this Fn is not in linear way. This is non-linear, non-polynomial way. Maybe some logarithms are there which are multiplied by our n value. So when the logarithm is there, simple master method is not applied directly. We use some extension value. What kind of that extension? Firstly, Fn is something in this particular form, and here the k value is representing the three way. If the value of k is greater than -1, equal to -1 and less than -1. These are the three cases. Then simply these are the simply answers. Okay. So by using the examples, we are just, we are understanding what was that extensions. So in this particular question, this is the given recurrence. In this particular recurrence, we are watching the Fn is not in polynomial way. Some logarithm values are there, non-polynomial things are there. So we are just applying the extension of the master method. Firstly, we have to find the value of A, B and Fn and just calculating the value of Gn, which is n. Now, comparing this Fn to the Gn, as we see, as we are thinking or seeing, Fn is not polynomially larger than Gn, so we have to apply the extension. So what was the extension? Just seeing the value of k, here the value of k is 1, and we are see na, the value of k, if the value of k is greater than 1, then case 1 is arises. Simply we are just putting the k plus 1 value. So in this particular solution, what we are doing simply the power of log plus 1, then n to the power log base ba, the value of that which is n, already calculated n, and the power of log k plus 1, the value of k is 1, then 1 plus 1 is 2, then the answer is n log square n. We are just watching the another example. Here the value of A, which is 4, and the value of B, which is 2, and the Fn is n square log n. Here the value of k is 2, which is again greater than 1. Simply बिल्कुल जैसे पिछला question था, we are just doing what? We are putting the value of this particular thing, which is n square, and just plus 1 the power, and already the power of k, which is 1. So we are just going to 1 plus 1 log square n. In the next example, little bit harder I am taking. The value of A is 2, value of B is 2, and what is Fn? Here log n in divided, we are just move up, then the value of log is -1. Here, the case 2 arises when the power is equal to -1. So, by the case 2.1, we know the solution. The solution is log n to the power log base BA, and the value of this particular thing already calculated. The value is n, and log n. One thing remember over here, this is not a log square, actually log n of log. So, simply the answer is n log n, and log n. Okay. So, in this particular lecture, we are just thinking about discussing about the recurrence, what was the recursion, what is the recursive equation, how we are calculating the recursive equation from the given code, and after that we are just taking view about how to solve this particular recursive equation by using the master method, and also we are discussing some issue in master method. What was that? If the Fn or a Gn, when we are comparing, then Fn is not a polynomially larger and polynomially smaller. We can say some gaps are there. So, we have to apply some extension value to solve these particular equation. In our next video, we are coming with another example of solving this recurrence. Okay, Jai Hind everyone.